Aircraft come in all shapes and sizes, and their applications vary hugely. Some soar distances of over 15,000 kilometers, while others reach speeds of over 7,000 kilometers per hour. Each aircraft has been optimized for a purpose, whether that be carrying passengers across the globe or dogfighting. And crucially, the engine will have been tailor-made for that exact purpose. After all, without engines, an aircraft is nothing more than a glider, or rock. So how do engineers at companies like Rolls-Royce and General Electric design modern aircraft engines? And how do those engines end up being so different from one another? We'll start with the most simple type of engine and run through a crash course of the key design options that have evolved over time to optimize engines for different applications. Let's start with the basics. The jet engine is the technology that underpins the majority of modern aircraft propulsion systems. A jet engine has a continuous throughput of air and a constantly burning flame. This is unlike a piston engine used in a car, where combustion only occurs during one of the 4 cycle strokes. The earliest jet engine was designed by a legendary Frank Whittle in 1932 and was eventually produced by Frank Whittle's Power Jets Company in 1941 as the W1, and it was used in the Gloucester E-28 aircraft. This engine had a single shaft, a single compressor and turbine disc, and utilized a reverse flow combustion chamber. What are these components? Simply put, a rotating shaft runs through the engine and links the compressor and turbine together. The compressor draws in and compresses incoming air. Fuel is then injected into the pressurized air and ignited. The turbine extracts energy from this process, which in turn drives the compressor. The remaining exhaust gas is blown out the rear to create thrust. Check out my video on how jet engines work for more detail on this. Frank Whittle's creation was a lightweight and compact configuration, but it was thermodynamically inefficient. And so began the race to improve efficiency and therefore aircraft range and speed. A lot has changed since the days of Whittle's invention. Let's take a look at some of the key design options that engineers now have up their sleeve. Frank Whittle's engine had a radial compressor, meaning that the air is spun outwards and compressed. This is a good solution, but results in an engine with a large diameter. Enter the axial compressor. First run in 1940. This compresses the air in the same direction that it's flowing. By stacking multiple compressors together, also known as stages, you can create a good pressure ratio and significantly reduce engine diameter. This is important, since aerodynamics dictates that airframe structures be thin and sleek. The majority of large engines you see on commercial aircraft use axial compressors. Next, we have the option of the number of stages. Stages are the bladed rows of compressors or turbines in the engine. This engine has 9 stages of compressors and 3 turbine stages. The more stages we have, the greater the compression ratio. The greater the compression ratio, the higher the engine's efficiency and the more thrust it produces. However, the more stages we add to an engine, the heavier it gets. There are trade-offs here between weight, efficiency, and cost. We usually need more compressor stages than turbine stages. This is because if we compress the air too aggressively in a single stage, the boundary layer flow could separate off the blade, and since the air is moving in a direction of increasing pressure, may reverse backwards in the opposite direction, causing a surge, such as this. In a turbine, the flow is moving in the natural direction of decreasing pressure, with no consequence to flow separation. Therefore, we can extract much more power from a single turbine stage. For efficient engines which operate with high pressure ratios, we typically need many stages of compressors. For example, the Rolls-Royce Trent 1000 has 15 stages of compressors to achieve a 50-to-1 pressure ratio. It then uses 8 turbine stages to efficiently expand the combustion gas. Military aircraft, on the other hand, often only have 1 to 3 turbine stages to improve their power-to-weight ratio. Industrial gas turbines are not constrained by weight and therefore have many stages. As you increase the number of stages, the rear compressor stages will want to operate at a much faster speed than the earlier stages. This is because the air is being forced through a progressively narrower channel, and due to the conservation of mass, must therefore speed up. To enable this, engineers can split the stages over 2 separate shafts, each running at a different speed. The shafts run one inside the other, as shown in this model. Notice how the shafts aren't physically coupled. The inner shaft is attached to the outer stages and rotates more slowly. This is known as the low pressure shaft. The outer shaft is attached to the inner stages and rotates more quickly. This is the high pressure shaft. The Pratt & Whitney J57 was the first twin-spool engine to run in 1950 and was used on the B-52 Stratofortress. You can even have 3 shafts for further optimization, like in the RB199 engine on the Tornado aircraft. The thrust mechanism is arguably the biggest consideration. The jet engine is simply a way of producing fast-moving exhaust gases, but there are many options for what to do with this exhaust flow. The simplest option is to quickly exhaust the gas and, using transfer of momentum, power the aircraft forward. However, you could install yet another shaft attached to a free power turbine. This is a turbine at the rear of the engine which isn't connected to an engine compressor and simply extracts the energy from the gas path and turns it into shaft power, which in turn rotates a propeller via a gearbox. This is what powers helicopter rotors and large turboprop engines. For example, the C-130J Hercules and A-400M both have turboprop engines. This is also a common choice for smaller aircraft. You could alternatively link the free power turbine shaft up to an electrical generator to produce electricity. This is basically how a gas-fired generator works and is also what some ships and aircraft carriers use as backup power sources. Yet another option is to spray more fuel into the exhaust gas and use a variable nozzle to create an afterburner, providing a lightweight method of almost doubling the thrust produced. This method is often used on fighter jets. The Concorde also used afterburners for takeoff. Up until this point, we have been talking about turbojet and turboprop engines. However, there is another major architectural option we have. This is the bypass ratio. Simply put, the bypass ratio is the ratio of air flowing outside or bypassing the combustion chamber divided by the air entering the combustion chamber. Having bypass air creates a turbofan engine. This requires a further compressor which delivers air to the bypass. This compressor is known as a fan and is what you see at the front of most large commercial aircraft. Increasing the bypass ratio improves engine efficiency. This boils down to the fact that it is more efficient to move a large volume of air slowly rather than a small volume of air quickly. These high bypass ratio engines are also relatively quiet. Over the years, engine bypass ratios have been increasing. The Boeing 747 was powered by the Pratt & Whitney JT9D engine, an early turbofan engine. It had a diameter of 2.37 meters and a bypass ratio of 5:1. Meanwhile, the GE90 engine has a diameter of 3.3 meters and a bypass ratio of 9:1. The Rolls-Royce Ultrafan demonstrator engine has a bypass ratio of 15:1. And that's it, we're ready to design an aircraft engine. If you found this video insightful, please subscribe for more videos in the future and let me know in the comments below what you'd like to see next. Thanks for tuning in today, and I'll see you next time.